Okay, great. Welcome back. We're in the home stretch now about this radiation law stuff. We are looking for ways, we've talked about energy and power, power being the rate at which we are moving energy. It's not so hard to think that a light bulb is somehow giving off radiation. Once you know that radiation is about things like light and infrared radiation and so on, okay, I see a light bulb, I can believe that it is giving off radiation. We don't like the word giving off. Let's say emitted. It emits radiation. And it's not so hard to picture that that light bulb is in some sense transferring energy to the world around it. It is transferring energy in the form of light, which will eventually end up like in your eye, and you'll be able to see with it. Or it's creating some infrared heat, infrared radiation that maybe as you get close to the bulb you can feel with your hand, and you can feel that it's transferring energy from the bulb to your hand. And that energy, of course, is in the form of these waves in the electromagnetic field / photons, whichever parlance you feel more comfortable with. That is how it's doing it. It is transferring energy in the form of these waves. You know what else is transferring energy in the form of waves? The sun. Here I have the sun setting, and the sun is producing electromagnetic waves which emanate out from the surface of the sun, cross 95 million miles of empty space, and come to the Earth. And when they come to the Earth, things might happen. They might get be used to warm the air, they might be used to warm the ground, they might be reflected off the ground. We'll have to decide what the fate of all of this radiation is, but the basic idea that the sun is emitting photons and transferring that energy to the Earth makes some measure of sense. In fact, it is the primary way in which we get energy to the Earth for climate purposes. Okay? Emitting photons extracts energy from the sun. The photons, or the waves in the electromagnetic field, carry that energy through cold dead space all the way to Earth, and then things will happen at Earth to that energy, like it'll get absorbed by clouds, or it'll get reflected by the surface, or we'll have to decide what can happen to all that radiation. It's also not terribly surprising then to find out that when heat is transferred from one object to another by radiation, one of the things that can happen is it can be absorbed by the object that is the radiation is encountering. When you are outside on a sunny day, heat from the sun was used to create these photons. They transfer energy to your body across 95 million miles of dead space, and when your body absorbs those photons, your body warms up. Your internal energy is increased by the act of absorbing those photons. That's what's happening like here with these cute little chicks here. Okay, they are under a heat lamp. The heat lamp is producing infrared radiation that then captures energy from the hot filaments inside of that heat lamp bulb down to the fluffy feathers of those cute little chicks. Okay, it is a transfer of energy. It extracts energy from the hot thing, the filaments of the heat lamp, and when the radiation is absorbed by the fluffy little chicks, they warm up. It's not so hard to picture this when we're talking about the sun or a light bulb or whatever, but actually everything emits radiation and everything absorbs radiation. It's part of what it means to be matter. And, you know, we're all made of matter. We are all the time, you, me, the walls, the room, the book in front of you, the computer, everything around you is emitting radiation all the time. And everything around you is also absorbing radiation that is coming, you know, into its environment and encountering it. Now, your book asks a really interesting question then. If everything around you is emitting radiation, why doesn't everything around you glow like a light bulb? I mean, apparently, I right now am emitting radiation. You are emitting radiation. How come you're not glowing? Well, the book actually kind of provides its own answer. It says, an object emits photons with a wavelength that is determined by the object's temperature. Depending on the temperature of the object, you're going to get a different wavelength of radiation that object is emitting. Now, as it happens, at the temperatures associated with like room temperature around you and body temperature and so on, the wavelengths of radiation that you or the books or the table or the computer or whatever are emitting are not wavelengths that are visible to the cells in the back of your eye. So it's not that the table in front of you isn't emitting radiation, it's that it's emitting a type of radiation that you don't have eyes that can see. But that doesn't mean that there aren't pieces of equipment that can measure it, or visualize it or whatever. And to help you understand that, I've copied out of here, this is a set of 3 figures that come from your textbook. And what I want to do is I'm going to examine each of these 3 diagrams right here. Each of these is a graph that shows the amount of radiation an object with that given temperature is emitting at a range of different wavelengths. So see how up in the top right corner it says 300 K? So this is for an object that has a temperature of about 300 K. That's right around room temperature or body temperature. It's like in the 80s of degrees Fahrenheit. And see, there's a range on the x-axis of wavelengths. And then that curve shows you about how much radiation is being emitted at like 5 microns. A micron is a millionth of a meter. That's that wavelength. A certain amount of 10 microns, a certain amount of 15 microns, and so on. It makes a little distribution like that. The y-axis, let's not worry about that right now as to what it means or whatever, other than it's more or less. Okay? As the higher up that line is, the more radiation is being emitted at that wavelength, and the lower that line is, the less that's being emitted at that wavelength. These curves are what are known as the black-body curves, the Planck function curves. We'll talk about that term in just a little bit. What I want you to see here is that an object that is about 300 Kelvin, which is about the temperature around your room right now, the walls, your table, whatever, actually emits radiation at a very wide range of wavelengths. Anything from about 5 microns out to, well, at least 20 microns as far as that curve goes on the graph there, but I mean it goes much farther off to the right. A very wide range of different sizes of wavelengths are being emitted by that object in front of you right now. But it is true that there is a peak wavelength. There is a wavelength of maximum emission, to use the right term. The wavelength of maximum emission, or lambda max, remember we're using the symbol lambda to mean wavelength. Lambda max is a particular wavelength that looks like, in the case of an object that is 300 Kelvin, that wavelength is about 9 microns. That is the wavelength at which the most radiation is getting emitted. Okay, so there's sort of this bell-shaped curve, or a puppy under a rug type curve, but there's a peak. There's a peak to this curve around, in this case, around 9 microns. Now see that bar on the side there where they colored it in gray? That is the range of visible wavelengths. They didn't label them on the x-axis there, but that would be 100 Kelvin. The curve is the radiation that object is emitting. It's way to the right of that range of visible wavelengths. The wavelengths that the object is actually emitting is nowhere near the range of wavelengths that a human eye can see. Oh, so I mean, it's not that that 300 Kelvin object isn't emitting. A 300 Kelvin object is emitting radiation, but it's all emitting at radiation at wavelengths that are longer than the wavelengths of visible light. You and I can't see them, but that doesn't mean we can't make instruments that can measure them, like an IR camera. An IR camera measures infrared radiation instead of visible light, and an infrared camera can actually look down and see, like for example this picture of these hands here, where they're seeing the different temperatures of different parts of the hands. How do they get temperature from that? They're figuring out based on, well, one of the ways they could be doing it is by, at each pixel, they're seeing what is the wavelength of maximum emission, and from that they say, oh, look, it must be this temperature. But anyway, I mean, this camera is clearly measuring infrared radiation in some sense. Let's do the same thing, but for an object that is vastly hotter. If 300 Kelvin is like, body temperature, room temperature, a little warmer than the average temperature of the Earth, etc. How about 6,000 Kelvin? 6,000 Kelvin is really close to the temperature of the surface of the Sun. Alright, so once again, statistical mechanics and quantum mechanics and so on can give us these Planck curves where we can compute what the amount of radiation emitted at each wavelength should be. Here's the curve for an object that has a temperature of 6,000 Kelvin. And again, we have this curve, and again, there's a range of wavelengths over which the object is emitting radiation, but you can see that much of this radiation is now inside of that little gray bar, which corresponds to the range of wavelengths that are visible light. In fact, a whole lot of the total radiation that's being emitted by an object that is 6,000 Kelvin is in that range. Remember something that's 6,000 Kelvin? That's approximately the temperature of the Sun. That's not a coincidence, right? The Sun is emitting a whole lot of radiation, and it made sense for us to evolve eyes that can see that kind of radiation. It doesn't make sense for us to evolve eyes for a type of radiation that there isn't much of around here. it's not surprising that human eyes are evolved to see pretty much the big chunk of radiation that's what the sun gives off. There is, again, a wavelength of maximum emission, lambda max. In this case, it's right around 0.5 microns. And that's a whole lot shorter than the wavelength of maximum radiation was for the object that was 300 Kelvin. The object that was 300 Kelvin had a wavelength of maximum emission right around 9 microns, or about, what would that be, 18 times longer of a wavelength than this. Huh. So once again, that 6,000 Kelvin object is emitting at that very high temperature, and it's emitting a whole lot of its radiation in the form of visible light, which is not terribly surprising. That is how the sun works. It's emitting radiation, and it happens to be mostly at wavelengths that are in that visible range. Same with like the filament inside of a light bulb and other things that are producing light. So I go back here. We saw the top and the bottom of these 2-3 panels in more detail. The right word for these curves is that they are the blackbody radiation curves. Blackbody. I don't want to get too bogged down by this here, but blackbody is a term that physicists use to mean perfectly efficient. This object is emitting as much radiation as it's capable to emit at its temperature. And this is the curve for a blackbody. Real objects are not blackbodies. Real objects will be emitting a little bit less, potentially a lot less at each of these different wavelengths, but we'll get there when we start talking about like the greenhouse effect and so on. But these are sort of idealized curves, okay? They come to us from like deriving equations about how much radiation an object should be able to emit at different temperatures. But look at the pattern. The top panel was for 300 Kelvin, the middle panel was for 1600 Kelvin, the bottom panel was for 6000 Kelvin, and on those 3 diagrams, heavens, the scale had to keep changing because lambda max, the peak of the curve, kept moving to the left. As the temperature increased, lambda max decreased. The hotter the object was, more and more of the radiation was being emitted at shorter and shorter wavelengths. And there's a word for that. That's called Wien's law. Wien's law, W-I-E-N-S, Wien's law. And Wien's law specifically says that the hotter an object is, the shorter the wavelengths of radiation that it tends to emit. And there's actually even a little equation for it, where it's got 3,000, that's actually an approximation of the real number, divided by the temperature gives you the wavelength of maximum emission. In that equation, to use it right, the temperature has to be in Kelvin, and then you'll get a wavelength of maximum emission that's in units of microns. But if you plug that in, you get the wavelength of maximum emission, and that comes to us from an old dead white guy of science, Wilhelm Wien, Wilhelm Karl Werner Otto Fritz Franz Wien, who was a German physicist who got the Nobel Prize for figuring out Wien's displacement law, which is where that term comes from. And yeah, it gives us a powerful tool to talk about the wavelength of radiation that an object is going to emit. Remember, wavelength is what's determining the type of radiation this is. Is this infrared? Is it ultraviolet? Is it visible light? Is it microwave or whatever? And Wien's law tells us that what's going to determine that kind of radiation is going to be the temperature of the object doing the emitting. Objects that have terrestrial temperatures, like the kinds of things you observe on Earth, you know, the ground, the clouds, the air, you, me, etc. Terrestrial objects tend to emit long-wave radiation. Their lambda max will be in the range associated with things like infrared radiation and microwave and so on. Whereas the sun emits mostly shortwave radiation. The sun is thousands of Kelvin warmer than the surface of the Earth was. By Wien's law, it's giving off radiation this vastly, vastly shorter wavelength. So here I need to introduce here 2 synonyms. When we say long-wave radiation, we'll kind of be sloppy and change back and forth between saying long-wave and terrestrial radiation. The radiation being given off by things around here on the ground, like the ground, the surface of the ocean, you, me, clouds, air, etc., things that are in our world, is going to generally be terrestrial radiation or long-wave radiation. Whereas the synonym for the short-wave radiation being given off by the sun will be solar radiation. So things like light and ultraviolet radiation will be short-wave radiation or solar radiation. Things like infrared radiation, microwaves, etc. will be long-wave or terrestrial radiation. So Wien's law is telling us what type of radiation is being emitted, and it tells us that what determines the type of radiation is actually just the temperature of the object that's doing the emitting. Seems like Another part of the story, though, is going to be how much radiation is being emitted. What determines the fact that, I think you probably don't need much convincing that the sun is giving off more radiation than your light bulb is, and that's giving off more radiation per unit area than you are, and so on. Well, in all these cases here, when I showed you these three curves earlier, the total power being emitted by the object is actually the area under the curves. If you survived like calculus at some point in your education or whatever, this is literally as in like the integral under that curve. Okay, the area under the curve is telling us how much power is being emitted in the form of radiation by this object. But these three curves here, if you look at their y-axis now, are radically different. They don't notice that the bottom graph not only does it have a different scale than the top graph, but the top graph is in, like, as it goes from 0 to 30, the bottom one goes from 0 to 100 million of whatever the units are in this diagram. These scales are radically different. It works a whole lot better if we pick some scales, some of these same curves, and we put them on the same black body graph. So we have 1, 2, 3, 4 curves on here for 4 different objects. Now it turns out, if we had stuck with having one of these curves be 300 Kelvin and one of these curves being 6,000 Kelvin, either we'd see the 300 curve and the 600 one would be sticking out the top of the graph, or the 6,000 one would be fitting on the graph, but we wouldn't even be able to find the 300 because it'd be so small. Let's pick a narrower range of temperatures here rather than 300 to 6,000. How about, like we did here, 1,000, 1,200, 1,400, and 1,600 Kelvin. So this is still a pretty big range of temperatures here. And when you look at those curves there, one of the first things you see is Wien's law. See how each one, as the object gets hotter, the wavelength of maximum emission is shifting to the left on the diagram? As the objects are getting hotter and hotter and hotter, they are also, the peak wavelength, the wavelength of maximum emission, lambda max, is getting smaller and smaller. Okay, that's just Wien's law. Makes good sense. But notice that if we're thinking of the whole area under each of those curves, between the curve and the x-axis, notice how much bigger these curves are getting and how fast they're getting bigger. The curve for an object that's 1,000 Kelvin is really, really tiny compared to the curve for 1,600 Kelvin. The object is emitting more and more more and more radiation, the hotter it is. And in fact, it gets more and more radiation being given off faster and faster. Look how much bigger 1,600 is than the curve for 1,000 Kelvin. Oh my goodness, it's getting big fast. There is a word for this law. It's the Stefan-Boltzmann law. Your book actually somehow manages to do this without talking about the term Stefan-Boltzmann. But the Stefan-Boltzmann law is the law that says the hotter an object is, the more radiation it's giving off. And it comes to us from two names, Stefan and Boltzmann, who discovered the laws independently within a few years of each other. Joseph Stefan, he was a physicist, mathematician, and poet in the Austrian Empire, according to Wikipedia. I didn't know anything about that guy before that. And then there's also Ludwig Boltzmann, who was an Austrian physicist and philosopher, who also has the most awesome beard, but that's another story, who discovered this independently using completely different assumptions and so on. But both of them correctly determined that the hotter the object is, it emits more radiation than a colder object does. And in fact, there's a fairly straightforward rule about such things. E equals sigma t to the fourth. E is the total amount of radiation being emitted, is equal to sigma t to the fourth. Sigma is just a constant, the Stefan-Boltzmann constant, perhaps not that surprisingly. Just a number that Stefan and Boltzmann both discovered. And t to the fourth power, the temperature to the fourth power. Woo, to the fourth power? Anytime you make t even a little bit bigger, t to the fourth power gets way bigger. No wonder this worked out that way then, that as temperature went up, not only did the amount of radiation the object emitted go up, it went up a lot, because it's proportional to t to the fourth power. Wow, that's a whole lot of energy being emitted the hotter and hotter the object is. Well, of course, we have one important thing in our corner of the universe that gives off a whole lot of radiation. That is the sun. It's 6,000 Kelvin. It's giving off enormous amounts of energy per square meter of the sun, but it's also 94 million miles away. Its role in the climate will be important, but fortunately we also keep it 94 million miles away. Now, over the course of the rest of this module and part of the next module, we're going to be talking a lot about the energy budget of the Earth in terms of how heat comes to the planet and how we get rid of it and how that affects the temperature and so on. I happened in this particular case to be using a diagram that illustrates it from NASA, but it could have been any number of different sources here. But what I want you to draw your attention to here is, okay, up there in the top left corner of the diagram, we've got the sun. The sun is emitting radiation, shortwave radiation or solar radiation, mostly in the form of visible light, also ultraviolet radiation and so on, which extracts energy from the sun and sends it out into cold dead space in the form of photons of light and ultraviolet radiation and so on, waves in the electromagnetic field. That radiation transfers through millions of miles of cold dead space in the form of shortwave radiation, and eventually some of that radiation is going to end up at the surface of the Earth, warming it up. I mean, we said absorbing radiation, being the thing that's up there and blocks that radiation and stops it, absorbs the energy that was in the waves or energy that was in the photons is now used to increase the internal energy that is the temperature of the object and warms the planet up. Fantastic. The Earth is made of matter. By Stephen Boltzmann's law, we know that it should be emitting radiation as well. The Earth itself emits radiation. By Wien's law, we know that that radiation should be long-wave radiation, stuff like infrared radiation and microwave radiation. So the Earth itself emits radiation in the form of long-wave radiation, which will go up through the atmosphere and carry heat and energy off into interplanetary space, where it's gone. We get radiation from the sun in the form of shortwave radiation that transfers heat from the sun into the planet, and then the surface of the planet emits that radiation back up into space in the form of long-wave radiation. And if everything were in balance and that was all there was on the planet, those two amounts would be the same. We would be getting as much radiation from the sun as we are losing back to space in the form of long-wave radiation, and it would be simple. Oh my word, look at that diagram. There's like 13 other things on that diagram. All these other processes like radiation reflected by clouds, absorbed by the atmosphere, emitted by clouds, evapotranspiration. Oh my word, there's all these other processes going on that are part of the Earth's budget too, energy budget too, complicating the final answer of how much is the internal energy of the surface of the Earth changing. How much is the temperature of the surface of the Earth changing? Woo! All right. I think we have something to keep ourselves busy for the next couple of lectures, figuring out this whole story of Earth's energy budget. Whew, okay, before we move on though to a future lecture here, let's answer two more questions. Question 6. According to Wien's law, hotter objects emit blank radiation than colder objects do. A, more, B, shorter wavelength, C, less, D, longer wavelength. Oh, it's important here to keep track. Which one of those is Wien's law and which one does it say? Okay. More than one of those things is true if I'm not worried about which law it is, but I am worried about it. I want to know which one is Wien's law. Okay. Click on one of the 4 answers below this video to get some feedback before you move on to the 7th and final question.